Last time we were we were at this stage. Okay. Last time we finished talking about the general idea. We learned that this d hat is an estimate of d. So this is a disturbance rejection happening here. D hat minus d hat plus d is going to have a disturbance rejection. And we talked about this by itself is not implementable, it's not causal, and we have to design Q, for example, as a low-pass filter to make everything implementable. Now, as a review and as a more rigorous analysis of everything here, I want to derive now. First of all, let me ask you a question. If you regard this as this is a feedback system, you see there's a feedback inside. If you regard this feedback system, regard V as the output, and all these as an input, you see, this is a 3-input, 1-output system. So you should be able to write down the transfer function like this. You should be able to write down the transfer function between U star and V, D and V, and psi and V. So you should be able to write down these 3 transfer functions. Now, there are multiple ways to do this. In the reader, it's just a regular analysis. You write down all the signal components inside this feedback closed-loop system, and then derive the transfer functions. The results is listed over here. Now, I want to go from a different approach to hopefully give you some idea of how we can do very quick block diagram analysis. So this is part of the topic of code. This is not in the reader, so you might want to write it down. Block diagram analysis. Let me start with something very simple. If you have G in the feed-forward path, and this is identity. This is a very simple negative feedback loop. So you know that you know it very well. This is equivalent to this. Okay? The closed-loop transfer function over here is G divided by 1 plus G. Now, if you have a little simple modification, if you have identity block here, then feedback block has G here. What is the transfer function? What is the overall transfer function between the input and the output? What's the transfer function between? All these cases, I'm deriving transfer function between 0.1 and 0.2. Okay. What is this one? 1 over 1 plus G, right? What about you have positive feedback loop? This is plus. Then you have 1 divided by 1 minus G. Okay, so that's very good. These are very fundamental, but if you use it well, it can bring significant simplifications in the analysis. Okay, so last one. The last one is also should be straightforward. If I have 2 paths, G1 and G2, then you know it very well. I am going to have equivalently is G1 plus G2. Okay, so as a review, remember these structures, the equivalence between these block diagrams. Now, I'm going to do one thing to make the DOB loop look like things like this. Okay, so look at this feedback block diagram. I can, first of all, I'm going to write down the first level of equivalence. This is D. This is the same G, U, V. Look at U. Starting from U, there's a path between U there is this feedback path. So I'm going to have U going through QS, and then come back here. The signs would be, I have negative here, and I have another negative here, right? So in the end, I would have positive feedback here. I have two negative signs, so I have positive feedback here. Now, look at this direction here. Starting from V, I have another path going from V to here, this summing junction, and then to this inverse nominal system, then to Q. And this path is also going to over here. So I'm going to have, starting from V, I have 1 divided by GUVN. And then going through Q, going through this summing junction here. No, I don't need this. Going to this summing junction here. Okay? Is this negative feedback or positive feedback? This line. What sign should I put here? This is positive, so no change of sign. Positive, no change of sign. The negative. So it's negative feedback for here. So these two are equivalent. Okay? Any questions? Some of you looks confused. So let me do it again. Essentially, I am doing this. Essentially, I am doing, first of all, I am distributing this Q into these two branches. So similar to the last time, I'm doing this Q negative plus Q 1 divided by GUVN GUV. So this is the first step. So look at this. This Q going through these two branches. And then take a look at these two local loops. I have one little local loop. And then I have another little local loop. These two, I'm just writing it in a separate way. This is the first local loop. And then this is the second local loop. Okay? So if you don't have questions for this part, now you see everything becomes very much simplified. Look at this little mini loop. What is the equivalent transfer function of this guy? So I'm looking at so suppose this is this part. What is the equivalent transfer function? Everything is the same. What is this guy? We just reviewed this guy a few moments ago. Exactly, 1 divided by 1 minus Q. Okay, because you can look at this way. Look at this summing junction here. If I add this signal here, it's equivalent to I'm adding the signal here. Okay, so adding it here is the same as adding it here. Just to add the signal to this branch. Okay, now inside you see this mini feedback loop with positive feedback over here. So which is equivalent to, as we reviewed earlier, 1 divided by 1 minus q. Okay? And we have the disturbance going into here, d. This is v. This is u star. Okay? So with this guy, you can very easily derive the transfer function between d and v. What would be that? The transfer function between d and v over here. Someone can very quickly just directly say it out. GUV. What's the bottom here? So it's a negative feedback system, so it should be 1 plus something, right? And that plus is the feedback gain, open loop gain of the system. So it's going to be starting from GUV 1 divided by GUV n q 1 divided by 1 minus q. So let's simplify this a little bit. Multiply 1 minus q in the numerator and in the denominator. Probably also multiply GUVN. So we're going to get 1 minus q GUVN GUV. In the bottom, we're going to have 1 minus q GUVN plus q GUV. Okay? So this is going to give us just a little bit more simplification. We're going to get the result. 1 plus, depending on how I write it, GUVN plus q times GUV minus GUVN. Okay? So very similarly, you can derive all the other transfer functions from u star to v, and from this measurement noise psi to v. Okay, so anyone has any questions up to this step? All right. So if you don't have any more questions, just go back home and derive all the other transfer functions between these signals. You're gonna get the final result. Okay. So this is the final result in the block diagrams. We just derived G from D to V is going to be this guy, and G from U to V. Oh, probably it's best to write it. Oh, my notation is still correct. So be careful. The notation here, G sub UV naught means from actually U star to V. I'm using this notation, following the notation in the reader. Okay, so all these three transfer functions. What's interesting now is analyzing the situations. Look at this transfer function and see. Last time we discussed when q is approximately 1 and when q is approximately 0, what will happen? So let's take a look at this more rigorously. Last time we did the block diagram intuitions. Now look at these transfer functions. If q is 1, what will happen to g dv naught? G dv equals to 0. What does that mean? In this closed loop system, feedback system, the dynamics between disturbance and V is 0. What does that physically mean? So that means disturbance is rejected, right? Let's take a look at the case when Q is 0. What will happen to here? Q is 0. This is 0. Then this is gone. This will cancel with this. We're going to have G d V equal to G u V. Okay? So that means we are not doing anything in the feedback system. The disturbance, the original dynamics between the disturbance and the output is G u V. Now, this feedback system is not doing any disturbance compensation, which is easy to understand because Q is now 0, means this line is totally cut off. We're not doing anything. Okay? So do a little bit more observations of the details. Take a look at, for example, if Q is 1, what will happen to GUV? Let's do it all together. This is also an interesting point. GUV naught. Q is 1, then this will cancel with this guy. And then this will cancel with this. So we're going to have GUV naught. Okay? So that means this entire dynamics, which is what we saw last time, this entire dynamics between U star and V behaves simply like the nominal model of the system. Okay? So summarizing, if you analyze all the situations, if Q is 1, if Q is 0, you can get all these results. Q is 1, we have disturbance rejection, we have nominal model following, and then we have this dynamics between the sensor noise and the output. If Q is 0, basically DOB is essentially cut off. So it recovers, everything recovers to the original feedback system. Okay? So let me come back here. Now you have realized that one of the benefits, just looking at these results, one of the benefits is that your actual system, GUV, might be containing Planck uncertainties. So it's different from GUV naught, GUVN, nominal. However, by doing this disturbance observer design, you can recover, you can make this internal uncertainties somehow they disappeared, and all you see from this side of the system to the outside is just this nominal system. It's just this nominal model of the system. So that makes the design and design of feedback or feed-forward controllers much more simplified, because you know this guy, you know the nominal model, and you can design your controllers based on this nominal model now. One immediate question when looking at this result should be, if we do that, can we guarantee, like, what are the conditions that we can very safely do this part? Okay, so equivalently, if we do this, can we guarantee the closed-loop system is stable or not? We haven't discussed that yet, and that's the topic of this slide. So over here, if the actual Planck is different from the nominal Planck model, we have this uncertainty over here. And I want to analyze the stability robustness of this feedback system over here. Okay? This is pretty similar to what we did last time. Look at these 3 transfer functions, these 3 closed-loop transfer functions. So you see, all the denominators are the same. So the characteristic polynomial of the closed-loop system are coming out of assign the denominator to be 0. This is a characteristic polynomial, characteristic equation. Okay, then substitute the equation of GUV over here. Then you're going to have GUV nominal. This GUV nominal times 1 is going to cancel this guy. And then what's remaining, GUV minus GUV nominal, is going to be equal to GUV nominal times delta from here. So that's equivalent to saying this characteristic equation is going to be GUVN plus GUVN delta times Q equal to 0. Is it? Yeah, looks like this is typo free. That means I have a typo in the notes. Okay? So the characteristic equation becomes this guy. Any questions for this part? Now, what are the closed-loop poles from here? Not closed-loop poles. What are the stability conditions for the system? First of all, the roots of this guy has to be stable. Okay? And then the roots of this guy has to be also stable. So that means GUVN, the zeros has to be stable. Then plus, we need to analyze under what conditions the zeros, the roots of this guy will be stable. So look at this guy. Focus on 1 plus delta times Q equal to 0. Now, if this condition holds, if you evaluate the frequency response, like this, if under all frequencies, the magnitude, this is a complex number. If under all frequencies the magnitude is less than 1, take a look, see what will happen. It's like a complex number. A complex number plus 1 means the complex number minus -1. Then this complex number, its magnitude is smaller than 1 always. So that means it lies inside a ball whose radius is less than 1. Okay? So if this happens, you see, this guy is never going to be able to touch the -1 point. Impossible. This complex number is never going to be able to touch the -1 point. Very similar to a Nyquist analysis. If that holds, then the roots, the closed-loop roots from here are all stable. Let me be a little bit more specific. So let's review a little bit Nyquist analysis. So remember, when we do Nyquist analysis, we did this guy, right? We analyze how the Nyquist plot of this guy looks like. And over there, we reviewed this kind of concepts. If it's impossible for this Nyquist plot to touch, or for the simple case, to touch this -1 point, then the system is stable. It's a basic Nyquist analysis. And then here, things are exactly similar here. Considering if I want to analyze the roots of here, of this equation here, take a look at this complex domain. picture, then you see this is never going to be able to touch the -1 point. So that means this is a sufficient condition for the this system, this roots of this characteristic equation to be stable. Okay, so here are these are the robust stability conditions. First of all, you have to have a stable zeros for the nominal system, and then second, you have to have this inequality of Q. Now let's look at all this equation together and see whether it makes intuitive sense. This guy is equivalent to Q j omega, the magnitude, less than 1 divided by delta j omega. Okay, this is. We mentioned earlier that delta, the uncertainty of the system, this is a large at high frequencies. High frequencies. So what's this condition constraining on the Q? That means at high frequencies, delta is large. 1 divided by delta, then it's small. So at high frequency, we are requiring the magnitude of Q to be small. Okay? We mentioned a typical design of Q earlier, right? Q is a low-pass filter. At high frequencies, you see, we indeed have a small magnitude at high frequencies. So that's another intuition for why Q is a low pass from our design earlier. Okay, so these conditions you see actually. Now, from the application point of view, disturbance observers are usually designed this way. We have a plant, and then we can design disturbance observers. Usually, disturbance observers are combined with some other feedback design. We usually will have this. And then usually we implement actually two closed loop. The disturbance observer is the first sub-mini closed loop system here. And then we enclose it with another feedback design. And if we now need to design feed-forward controllers, we can simply do, for example, feed-forward design. We can let it be the inverse of this entire dynamics here. Now, this is the usual, one of the ways to do this. Okay, so pay a little attention here. When I use the transfer functions inside, pay attention to what I'm using. I'm using GUV nominal. So I'm using the nominal model of the plant in the feed-forward design. Okay, this is for the reason that we have analyzed earlier that with a disturbance observer, we can achieve nominal model following under certain design of Q. Okay? Because this entire dynamics looks like GUV nominal, then we can design it, feed-forward design this way. Some choices you may see that our GC can be a PD controller. Or some people will use LQ to design GC over here. And feed forward, some people may use zero phase error checking to design this feed forward design. Okay, so these are very common designs especially in motion control systems. Okay? So now we have finished the continuous time disturbance observer analysis. In the remaining of the class, I would like to talk about the discrete time case and then have a little review of what we have learned in the first part of this course. In the discrete time case, this is usually the way that is implemented. So besides every signal are now discrete time signals, we have discrete time plant, PZ. My notation for the plant is PZ. And then the nominal plant is PN. Okay? The relationship between P and PN look like this. So the actual plant is this nominal plant with some delays over here. And then we have the same structure as a Q here. Everything is very similar except that in the discrete time case, this is the usual case. We put this delay element on this path, and then everything else is exactly the same. So you can analyze in a similar way that what is the transfer function between D and Y, what is the transfer function between U star and Y. Okay. What are the conditions for the closed loop system to have disturbance rejection? Everything is very similar. We also need Q. Q can be low pass. One of the ways is Q can be a low pass, and the magnitude has to be small at high frequencies. These results equivalently hold in this structure. Okay. You can see more details by looking at this reference here in the discrete time case. And this is the only place where things are a little bit different. But other than that, everything is the same. So it is from here I want to talk about one thing. One thing that is very related to practical design. If I do similar analysis and write down the transfer function between the disturbance and the output, if I do similar analysis and I want to derive the transfer function between D and Y, okay, I would need to do, again, I will do similar designs. I will break this path, this mini feedback loop, and this larger feedback loop into two components. So I'm going to get this mini feedback loop. Let me do it very quickly. Actually, I just want to show you the result, but still, let me finish up the writing. So first of all, I am going to have a positive feedback loop here, this positive feedback loop. And then second, I am going to have this negative feedback loop, which is going to be Q1 divided by Pn. Okay? So now you can derive the transfer function now. What is the transfer function between D and Y just by looking at this block diagram? G D to Y. do a little bit computation. Then you're going to get, for the numerator, I'm going to have P. This is the direct path between D and Y. The denominator, I am going to have a negative feedback loop. So it's 1 plus, then the loop gain of the system, which is going to be Q, 1 divided by P and P. Then this transfer function here, the transfer function of this small block diagram system, which is going to be 1 divided by 1 minus C, negative MQ. Okay? You can do this from other ways, but I want to show you one result from where I hope you can have some feeling of actual control design. So simplify the computation, simplify the structures, we are going to get this final result. Okay? Now, look at this transfer function. My question is, if D is periodic, if dk equals dk minus n, how should we design Q to have good disturbance rejection? That's the question. Okay, so this is directly related to repetitive control. And now, we discussed 2 ways to do repetitive control design. Now this is the 3rd way. What's the condition for Q if I want to have good rejection of repetitive disturbance? Okay, so this is not written on the reader. Just imagine you are given this problem. How will you do based on what you have learned? Okay? So spend maybe 3 to 5 minutes, think about the problem. this is from the plant.
This comes from the plant?
Yeah. Yeah. So if you have a practical plant, the factor this as in this way, then this is whatever is the delay of the plant.
Oh,
Yeah.
I see.
It's kind of fixed. Yeah.
Okay.
So after you have have a little thinking about it, have a little, try to discuss this your ideas, your intuitions with your classmates sitting beside you, and have an exchange of ideas. Or if you have already find the answer, just raise your hands. What do you think? Figured out something in mind.
The idea is that the disturbance is going to be a constant.
Periodic, not constant.
Periodic.
Yeah,
Okay.
like what they did.
Okay. So it's periodic, and we want a Q.
Yeah, design Q.
The disturbance.
Yeah, design Q such that the disturbance is rejected in this system. So one thing you can take a look is the earlier result. What is the internal model of the periodic disturbance? More specific, what is AD? We mentioned D for the disturbance. What is something AD times DK will go to 0? Think about this way. Yeah. Okay. Anyone had some exchange of ideas? If you haven't, I will exchange ideas with you. All right. Anyone has a proposal now? What will be something Q can be? Okay. So let me do one proposal. We have learned the transfer function between D and Y is GD to Y. So that means YK equal to this guy, if I use Z as a delay operator, times DK. Okay? Then there will be other terms like G U star to Y, Z inverse times U star K. Okay? This is the disturbance rejection performance. This is how the signal follows the reference. So I said we are focusing on disturbance rejection. So we just need to take a look at the first term here. We have PPN divided by 1 minus Z negative M Q PN plus QP. And then 1 minus Z negative M Q DK plus this second term, which I don't need to worry for now. What is the condition? What is one condition that will make this go to 0 if DK is periodic? These guys, PPN, probably we don't have much design freedom here. We have the design freedom for Q. Now, recall what you learned earlier in repetitive control. If dk equals dk minus n, then we have 1 minus z negative n dk equals what? Goes to what? 0. Okay? Now, look at the result we have and the conditions we need. So one way to do is just to do q equal to d, let me see, negative m plus n, negative capital N plus m. This would be one way. Okay? So it's really simple this way. We just look at the original block diagram and see what's happening. It makes intuitive sense. So it says if dk is a periodic signal, then we can just use some very simple delays. If we delay the signals very carefully, we will be able to have a correct phase, correct estimate d hat k that will cancel dk because it's periodic. So if we delay by a certain amount, it will go to exactly the same phase as the original signal. So that's one way to do. But this is not the only way, though. There are many other ways to do. And I want to give you the intuition for another design here. Look at this, this transfer function again. You see, let's do a very simple case, special case, just for intuition purpose. Let's just say P, we have a very good model. So if you see, take a look at the relationship between P and Pn. I said this is the nominal model for the plant. So that means we can actually have some more simplifications here. This transfer function equals Ppn divided by 1 minus q times d negative m Pn plus qp. So you see, this bottom part is actually very, very approximately 0. If we have p approximately equal to d negative m Pn. So this is approximately 0. And then we have d negative m q. Okay? So approximately we have this guy equal to ppn y minus d negative m q. Okay? If I use this design, design star, then we have ppn 1 minus d negative n. Look at this term. Look at this term. So if I have disturbance signal going into the system, so now I'm analyzing the picture I'm drawing is I have disturbance going into the system here, and the inside is this transfer function. The output is this guy g d to y dk. Imagine the case. Imagine you want to plot the frequency response of this guy when you do transfer function analysis. Imagine you want to see how the frequency response of this guy look like. Can you tell me what is the magnitude response? How the magnitude response of this guy will look like? Control problem. So you have designed something. Now you want to see how detailedly everything works, and then try to improve your design. So what will be the magnitude response of this newly added term look like? This is a little bit tricky question. So I'm going to have 1 minus So replace z with ej omega. E negative j omega n. This guy, what's the magnitude of this guy? It's always 1. It just has a phase angle. So it's almost like I have something always unit magnitude, but it's changing in phase. And then 1 minus this guy. So I have this point minus the points on the unit circle here. Okay? So what's the magnitude? What's the maximum magnitude for this complex number? 2, right? Is this guy minus this guy. What is the minimum magnitude? It's 0. So it's this guy minus this guy. So it looks like maximum is 2. Let's see. If I draw this, this is 2. This is 1. This is 0 in a linear scale. It's going to be at certain frequencies it's 1, it's 0, and then at some other frequencies it's 2, and in between it's a continuous function. So if you do this in MATLAB, this is what will happen. The important things you have already seen. We have some place where the magnitude is 0, and some other place magnitude is 2. What does it physically mean if I have 0 magnitude over here? So that means at this frequency, let me call it omega 0. That means at this frequency, whatever disturbance component at this frequency will be rejected, right? What will happen now for the disturbance signals at this frequency? It's amplified. See? Now you have exactly a practical design problem. You have achieved your disturbance rejection at certain frequencies, but unfortunately, you have amplified the signals at other frequencies. Okay, so if you are given this problem and asked to improve it, then you might want to think about how you can keep this 0 magnitude for disturbance rejection, and then in the meantime, how to reduce these amplifications here. Okay. So one of the way to improve it looks as follows. You want to design 1 minus z negative mq. Okay. This is the first design. We design it this way. Design number 1. Another design, I'll just give you the result and then show you how it works. Another design is to do as follows. I added something to the denominator. Okay? If you do that, and then again evaluate the magnitude response of this whole thing, and see what will happen. So you can break the magnitude into 2 parts. If you want to evaluate the magnitude response, you can do the magnitude response of the top numerator, then the magnitude response of the denominator. Z equal to ej omega. Okay, you have seen. Take a look at how this bottom part looks like. Again, draw this picture. Now things are a little magnitude of alpha n times z negative n is going to be, what's the magnitude for this guy? The frequency response. So that means alpha n e negative j omega n. This is unit, magnitude is unit 1. The magnitude of this guy whole thing is actually going to be alpha n. This length is, radius is alpha n. Okay? So is this guy, is 1 minus this guy. If I have 1 here, okay? So it's going to be 1 minus the points on this circle. Okay? So you see now, let me draw another picture for the demonstration. You see now, for the first guy, I am evaluating on this unit circle. So if I draw this unit circle here, this is unit circle, this is -1. So I'm evaluating here on this guy. And then here, I am evaluating, picture is too small, 1 minus this guy. So what will be now the case of maximum frequency response? What will be now the maximum magnitude for the frequency response here? It's going to be, draw a big picture, 1 and alpha n. I have a circle. And then I have another circle. Oops. I can't draw. So it's going to be, yeah, you just do this magnitude response evaluation. So imagine at first frequency, omega equal to 0, I am going to have 1 minus this point, and then, where is it? 1 minus z negative n divided by 1 minus alpha n z negative n. So it's going to be 1 minus this point, and then divided by 1 minus this point. So it's still 0 at frequency 0, omega equal to 0. So it means magnitude is 0. Okay. Now, as you increase the frequency is ej omega. So your z now equals to ej omega, and omega is non-zero. What you are evaluating is 1 minus this point. So it's this magnitude, the length of this vector divided by the length of which vector? Yeah, the question. Divided by the length of which vector? 1 minus z alpha n z negative n. What is that vector here? Here, right? So it's this guy. Okay? Immediately you see from this picture, is this magnitude division going to give me something? Yeah, this one is too obvious. This guy minus divided by this guy, the magnitude is less than 1 in this case. Let me do the extreme case. So we see from last time that the maximum magnitude for 1 minus z negative n is this point minus this point, -1 point. So the maximum magnitude is here. Now, take a look at the case, what will be now the magnitude at this frequency? So I have the numerator is 1 minus z negative n is this length. Is this length. What's the magnitude of the denominator? It's here, right? 1 minus alpha n z negative n, and z negative n is right in here. Okay? Oh, it's this guy. See, immediately what's happening here? Originally, I have a maximum magnitude of 2. Now, in this new approach, what's the maximum magnitude in this case? You can actually analytically write it down. 2 divided by this length. So this length is 1 plus this, 1 plus alpha n. So immediately you see you can change the maximum magnitude by tuning this alpha. Okay. So that's another way to improve the design. Okay. And if I finish up writing the picture, it would be like this. Originally, we have something like up and down with 0 at here and 2 at here. Now, in the new design, it will look like it will have smaller amplifications, and you can tune this amplification. Okay, so it would be something like this. Okay. And some of the details are in the references given to in the course notes. So, as a review, what we have just done is from this in these two last lectures, we discussed disturbance observers. We discussed how it achieves disturbance rejection, and then it's called nominal model following. Okay, we discussed how the design of Q should be look like. So we discussed at least two situations. First of all, it's a low pass filter. Okay, Q looks like this. And then we discussed for repetitive control. Okay, how a Q should look like. We discussed two designs. One is a simple delay element. Okay, and the other is the thing we just talked about. Okay. As long as you understand the first part, is fine. For the second designs, take as much as you can. But this is the only required part for this this repetitive control in disturbance observer design. Okay. And along this, we reviewed block diagram analysis. This is the thing I want you to really be very smooth about. So this is required. Analyzing a block diagram. Okay, I wish you to be able to very quickly derive the transfer functions between each different signals in a block diagram. Okay. Now, that's a quick summary for today's lecture. Write a new one. Overall, now starting from next time, we'll talk about something completely different. Starting from next lecture. Okay? Starting from next lecture is the second part 2 of the reader, of the course reader. So bring that one with you next time. We'll be talking about system identification and adaptive control. Okay? These are directly related to what we have learned so far. So far we have learned. If you think about this, some of you actually asked me this question, and it's a very good question. If you think about what we have learned, we learned LQ, we learned Kalman filter, we learned LQG, we learned LQG LTR. And what's the next topic we learned? FSLQ. What's following that? Internal model principle and repetitive control. And then disturbance observer. Preview control, yeah, I'm missing preview control. Preview control is somewhere here between these two. It's a feed-forward design and preview control. Okay, have a big picture of everything here. You will see that in all these designs, we need system model, right? Even if you are designing a Kalman filter or LQ, you need ABCD matrices. We haven't discussed how these are obtained yet. And in the next part of the course, we'll talk about how you identify a system based on the data you can receive, And if you don't have accurate information of the plant, how you can do control to adaptively make a good performance. Okay, that is what we're going to do next. So I would spend a few moments talking about the homework number 5. So in problem 3, I asked you to do like very short, 1 or 2 pages of proposal. I want you to be able to, now you have learned all these techniques. It's a good time to go back, to sit back and take a look at what are the conditions, under what conditions can we apply these design methods to a practical problem. So I want you to formulate a problem, pick out some topic, formulate a problem, read some literatures, try to formulate the control problem, and then apply something you have. And from my experience, this is extremely useful. To be able to formulate a problem is sometimes more important than having these techniques, these detailed mathematics to solve the problem. And I really want you to have a good training to do that. So you can work with some other classmates, like in a group of two students. Have a discussion and then read some literatures together, or find a topic that will interest both of you, and formulate the problem as the way I give you some standard procedures to formulate the problem. Okay, and if you have any questions, discuss with me and the GSI. Okay, probably I won't give you any specific literatures. You can pick out whatever you like and then read the topic and formulate the problem. And after you submitted the problem, this is the evaluation. So you are going to receive comments from the GSI and the instructor. You're also going to receive comments from your classmates, from your peers. Okay, it's like a peer review. I'm going to distribute your proposal to 2 or 3 students anonymously, and then let them take a look whether the proposal makes very good practical sense. Okay. So that would be all I have for today. So I think I'll hold office hours until 9:30 today, and then I will hold office hours in the afternoon, the regular office hours in the afternoon. You can feel free to leave now if you don't